Hello. So today we're going to talk about um, gravitational potential energy, but it's a general case, or maybe it's okay to say global case. Right? So it's not a local case, not a local case. Okay, so it's gravitational. Okay, so the form we're usually using U for gravitational potential energy, which is equal to, or for all the potential energy, is equal to minus G, the universal gravitational constant, and then times M1, M2 divided by the distance between M1 and M2. And there's a negative sign there. Let me circle that. So to remind you, there's a minus sign right there. So what does that mean? It's always less than zero, right? Less than or equal to zero, if you like, when r is equal to infinity. So that means we are defining all this gravitational potential to be negative. So it's always negative. So what does that mean? Always negative. It means that you are trapped, okay? We are trapped on the earth by the gravity, okay? So it means that we are trapped. 我们陷在里面 okay? In Chinese, it means 有陷在里面 okay? So when R is approaching infinity, so like far, far away from Earth, then that's when your U is approaching zero. Okay, so that's your maximum gravitational potential energy. So basically, you're saying the reference, right? So your reference of the U, right, of U, is set at R equal to infinity. Okay, that's all. There's nothing else different from when we say U is equal to mgh, okay? This mgh, right? It's just saying that the reference is at when h is equal to zero, okay? So that's like when you are at the sea level on the earth, and then your potential energy will be growing, right? Bigger and bigger. So, but that's not in the general case. We want to set the reference at a different point. So that's all. Okay. So that is the important distinction you got to make, right? So now, remember when we say PE is equal to mgh, right? One difference is this is a local, like a local mgh, local potential energy. Okay. The G is more or less has to be constant, right? That's when you're using this formula. If not, then this G, if G is varying, then this formula is not convenient, right? Not very convenient because it's changing. Okay, so only when G is constant we're using this form, and then remember the reference is at G, H is equal to zero. So it's kind of like this. We have the Earth, right? So you're right there. Okay, right on the surface. So this is the surface of the Earth. All right. So now let's talk about let's draw a curve for global potential energy. Okay, so I'm gonna draw like that. So this is the Earth. All right. So we're gonna do this. Okay, we're gonna say this is U. So U is equal to minus G M1 M2. So one of this could be the ME, right? Mass of the Earth. Divide by R, right? So this is the R, okay? So when R is equal to zero, right? Or approach zero, which is right there, right? This one become a negative infinity. So it's right there, down here. Okay, down here. It's going like this. The point is down there, okay? So this is when the R is approaching zero, right? So it's negative infinity. This is zero. This is positive infinity. This is negative infinity down there. So it's going like this. And then when R is equal to the Earth, okay, equal to the, when this R, when the R is approaching RE, okay, so it's like, this is RE here. This is RE, okay? So then this value is going to be U equal to minus G M1 M2, and then divide by RE, right? So this value is the 6,400 times 10 to the 3 meter, right? And this M1 is your mass. So let's say you are 100 kilogram. M2 is the Earth's mass, which is 6 times 10 to the 24 kilogram. And then you have the G, which is 6.67 times 10 to the negative 11, right? Then you come up with this in joule, right? So this unit is in joule. And just go in computer, you can see it's so 24 minus 11, which is 13, and then divided by 7, right? Divided by 1, 2, 3, 4, 6. Okay, so almost 7 because 6, 7. So it's going to be like a 10 to the 6 minus, right? So it's still a big number, but it's not negative infinity. So it's going to be like somewhere near here, for example. And this is my negative 10 to the 6, right? So roughly, okay? So it's kind of going like this. Oh, right there now. And then when it goes to infinity, when R is approaching infinity, then this one's infinity, right? So that's becomes 0. So then U is approaching 0 now. So 0 is right there. So this guy's going to keep going until R is infinity. All right, so it's right there, okay? So that's what it looks like, in this particular global gravitational potential energy, the shape of our unit, of our potential energy. It's looking like this. This is the curve, okay? So that's what, so it's always negative. See, that's always negative. See that? Always negative. So it's right there. Do it one more time. Okay? And when you do the MGH, it basically says the following. This kind of thing, doing this. Okay? And, if you doing the U equal to MGH, right? And this is your H. So this guy going like that. And the slope is equal to mg. Okay, so you can see clearly the two are not quite the same. But if you look at it in a small place, right, like from here to here, for example, like from here to here. So H is equal to 0. And this is some kind of H. H is equal to 2 times of RE, for example, right? 2 times Earth, so basically like that. Then, it's roughly like that, right? It's growing bigger. We know that. The trend is right, all right? But it's not quite a line. It will be a curve, okay? Right? If you do it correctly. So this is just approximation here for the U is equal to MGH. Okay, so that's all we have. And that's the local and the global gravitational potential energy. Thank you. And we'll see you